Year 11, homework 5. This is a rate of reaction homework, and let's get started straight away. So we've got magnesium reacting with hydrochloric acid. So there's the magnesium in the flask there and surrounded by hydrochloric acid. It produces hydrogen gas. So we've got a gas syringe here to collect that hydrogen, and we can measure how quickly the gas comes into this syringe because it'll have readings on the side. We can record that every 30 seconds. The hydrogen is a product, and that's how we can monitor the rate of most reactions by seeing how quickly a product is produced or how quickly a reactant is used up. First question, write a balanced symbol equation for the reaction. Well, I'm not going to do it for magnesium hydrochloric acid, that's your job. I'll do it for, say, calcium and nitric acid. So it is important that you know the formulae of these common acids. Nitric acid is HNO3. Hydrochloric acid, you can look it up on the internet, or you can work out the formula quite easily because it's made of hydrogen ions. And chloride ions. Chloride ions are in group 7 of the periodic table, so they have a single negative charge, and of course the charges need to balance. You do need to know the formula of the common acids: hydrochloric, nitric, and sulfuric. Sulfuric is H2SO4. Okay, write them out 5 times until you've learned them. Okay, they react. Okay, so they're going to react to make magnesium chloride. And again, you need to work out the formula of that. Magnesium is in group 2 of the periodic table, so it has 2 electrons in its outer shell. It wants to lose 2 electrons, it forms a 2+ charge. The chloride ion, group 7, it wants to gain 1 electron, have a Cl- charge. So that'd be Mg2+ and Cl-. Okay, here, calcium has a 2+ charge because it's in group 2 of the periodic table. And the nitrate ion carries a single negative charge, NO3-. So I'm only going to need 2 nitrate ions to make that balance, because that's Ca2+, and each nitrate ion is a 1-. 2+ and 1-, so I'd need 2 nitrate ions, hence I've got bracketed it and put 2 after. So that'd be calcium nitrate plus hydrogen. There's my equation. That needs balancing, so I only need a 2 before that, and that balances out. The important thing with balancing equations is to get the formulae right. You get 1 mark for the formulae of the reactants, 1 mark for the formulae of the products, and then 1 mark for balancing. So these formulae are really, really crucial. Okay, so that's not the answer. You need to do it for magnesium and hydrochloric acid. On the graph paper, plot a graph of the following results, include a line of best fit. Okay, so I'm not going to do that. You can plot your own, but basically your line of best fit at the end, if it doesn't look a bit like this, okay, so let's see if I can get the pen to work on that. If it doesn't look a bit like that, you've got it wrong, okay? So, you're going to have points, x's, which you're going to join up. There might be an anomaly. If there's an anomaly, you can miss it out, okay? And that's what this next question is, an anomalous result. An anomalous result is a strange result, or a result doesn't fit the pattern. So if this were my data and it's not my data, okay, you can see why that's an anomaly, okay? And we've missed it out because everything else is sort of smoothly on the line, but that point isn't. Acid is present in excess. What does excess mean? Well, basically we have 1 reactant in excess, means too much, so we get all of the other reactant to use up. All right, next question. If the same length of magnesium ribbon had been cut into small pieces, well, doing that increases the surface area. If you can make a solid smaller, it increases the surface area. Okay, so we've got the same length of magnesium. So I haven't changed the number of magnesium particles, we've just increased the surface area. Now that's important because that means the amount of gas isn't going to change because we've used the same amount of magnesium. If we'd increased the amount of magnesium, and remember the acid is in excess, so if we'd increase the amount of magnesium, we would get more gas produced. So we're going to get the same amount of gas produced because we've got the same amount of magnesium. Okay, but smaller pieces. Acid is the same before, sketched on the graph, what would we expect? So, if it's the same amount, it's going to finish at the same height. It's going to finish here. The reaction is going to finish exactly the same amount of gas given off. Okay, because if we wanted more gas, we'd have to start with more particles. We don't start with more particles. If we wanted less gas, we'd have to start with less particles. Okay, so it has to finish at the same point there. But we're using smaller pieces. Smaller pieces is a greater surface area. So we've got more particles on the surface, more particles exposed. So if we've got more particles exposed, we've got more room for collisions. That makes it faster. And remember, graphs, rate of reaction graphs, the steeper they are, the faster they are. So it's going to start there and it's going to finish there. You can connect the two of those and you need to label that. B. Next one, C. If the magnesium ribbon had been replaced by a piece twice as long. Okay, so now we've got double the amount. So if we've got double the amount, we're going to have to get roughly double the gas. So I finished that about 58, so yeah, about there, I suppose, yeah. So it's going to finish up there. Okay, now, if it's twice as long, is it going to be faster, slower, or same speed to start with? Well, if it's twice as long, we've got twice as many particles on show, haven't we? So it's going to go faster than the last reaction. So you can start that one off and finish it off, but have a go at that. Apart from the changes to the magnesium, give 2 ways in which the first experiment could have been slowed down. Well, there's 4 ways we change the rate of reaction. There's 4 ways that you can say to change the rate of reaction. One is concentration, okay? We can change the rate of reaction by changing the concentration of the acid. We can change the surface area, okay, but surface area is only for solids, and that's the magnesium, so that's not going to be the right answer. We can change the temperature, and we can add a catalyst. Okay, so pick the answers you like out of that for those ones there. Right. Next one, calculate the rate at the beginning of the reaction. Okay, so I've sketched a graph, so I'll do this assuming I'm on my sketch graph. So my answer is not going to be accurate. You need to do it yourself. Right, so rate is equal to the gradient at the start of the curve. Okay, now this is a curve, and we know how to calculate gradients as straight lines. So the first thing we need to do is get our ruler and put it on right at the very beginning of that curve. Okay, we put it at the beginning of the curve. So the ruler here matches the gradient right at the very beginning, and then we're just going to draw quite a nice long straight line. Okay. All right. Now it doesn't matter where. You could pick to go up at 20 or 40 or indeed anywhere on here. We just now need to draw up from this x-axis. So I'm going to draw it from 40 because that seems pretty, that's a nice easy number to read off the graph. And I'm going to rule up to the line. Now you do yours in pencil, please. Every time I'm doing mine in pencil doesn't show up very well in the video here. Okay, so where it touches that line, okay, we now need to draw it across to the other axis. Okay, so we've got an x-axis value and we've got a y-axis value. Now in maths, okay, you calculate gradient, okay, gradient, and you do this in GCSE maths. Gradient of a line is the difference in the x's, difference in the y-axis, divided by the difference in the x-axis. And that's exactly what we're going to do here with those numbers that we've just ruled off and found. So y-axis, we ended at 80 and started at 0, so the difference is 80. So our y-axis is 80, and our x-axis ends at 40, starts at 0, so our difference here is 40. 80 divided by 40 is 2. Now that's an answer, but now I also want a unit. Okay. Our y-axis unit is centimetre cubed, so we'll have centimetre cubed, divided by our x-axis unit, seconds. So that means the unit is centimetre cubed, divide is another way of saying it's per, centimetre cubed per second. So 2 centimetre cubed per second, line seconds. Okay, so there is that. That's my answer for my sketch graph. You need to do it accurately for your graph now. An equation for aluminium reacting with hydrochloric acid is here. What mass of hydrogen, so we need to put a question mark straight away on the hydrogen, is obtained from 270 grams of aluminium. 270 grams of aluminium. Okay? So I'm not going to do that question for you, but I have written out another one just here that is exactly the same, but just different. Okay, so exactly the same method. Okay, different numbers, different equation. Okay, so I said here an equation for aluminium reacting with hydrochloric acid, and this time I've got an equation for magnesium reacting with hydrochloric acid. So Mg plus 2HCl, MgCl2 and H2. What mass of hydrogen is obtained from 270 grams of aluminium and excess acid was the question here, and I'm saying what mass of hydrogen, let's put a question mark on that, is obtained from 12 grams of magnesium. I put right the 12 grams on top of the magnesium. Okay, so I'm going to do this one. Okay, now there's 3 stages to this. Stage 1, moles. These calculating quantities questions have 3 stages. Moles is 1. Second stage is stoichiometry. I'll explain that in a moment. And the third stage is moles again. So moles, stoichiometry, moles for calculating quantities. Okay, so in the first stage, we have to calculate the moles. We have to calculate the moles of whatever we have written the mass of. Okay, we know this is a mass because it has a unit after it, grams. So moles equals mass divided by atomic mass. If you want to write formula mass down there, I don't object to that. Okay, mass is the unit, the one with the grams, 12. The relative atomic mass is given in the question. The AR of magnesium is 24. 12 divided by 24 is 0.5 moles. That's stage 1 done. Give yourself a mark if you've got that far. Okay, next stage, stoichiometry. Well, this is the equation now. Now, in the equation, we had 12 grams of magnesium and excess of acid, so we can cross that out. We're not worried about the magnesium chloride, so we can cross that out, and hydrogen is the question mark, so we need that. So let's write that equation down here. Mg arrow H2. So I've only written it with what I'm interested in. So the equation, there's no number before the magnesium, so there's an invisible number 1 there. There's no number before the hydrogen, so an invisible number 1 there. So this stoichiometry of this equation is 1 mole of magnesium makes 1 mole of hydrogen. Well, we don't have 1 mole, we've got half a mole. So what you need to do is look at the relationship between these numbers. Are they the same or are they different? They're the same, aren't they? 1 in, 1 is the same. So we start with half mole of magnesium, so that's going to make the same number of moles, because this number here is the same number of moles as hydrogen. Now, in your question, those numbers are not the same. 2 aluminium, so when you do stoichiometry down here, let's help you with this because this is the hardest stage of all, but when you get the hang of it, it's not hard at all. Okay, so you have got 2 aluminium, arrow makes 1 hydrogen. There's an invisible number 1 there. 2 and 1. Are those numbers the same? No. Okay, so your next question is the hydrogen bigger or smaller? Well, 1 is smaller than 2. In fact, 1 is half of 2, isn't it? So whatever number of moles you start with, you're going to have to halve it to get the number of moles of hydrogen, because that 2 there is twice the size as that 1 there. So whatever number you have here, so if you have a 20 there, it's going to be 10 over here. If you have an 80 here, it's going to be 40 over here, because this is a halving relationship. That relationship there is halving. Okay? So whatever number you worked out for moles, plug it in down there, okay, and halve it to get the number of moles of hydrogen. Right. So that's stoichiometry. So the answer for stoichiometry is half a mole. For the first mole, can you see? For our first answer, it was half. Okay, that half went down to there. And that half now feeds over to here. So our next stage is moles again. Well, we've now found out we've got half a mole of hydrogen. Okay, so we need to use this moles equation again. Moles equals mass over atomic mass. But what we want to find is what mass of hydrogen. So we need to make mass a subject. So let's rearrange this equation. Mass equals moles times AR. So I've just rearranged that formula, okay, to make mass a subject. Moles, we know, is half, 0.5. Okay, hydrogen. The hydrogen molecule is the H2 molecule. It's made of 2 hydrogen atoms. 1 hydrogen atom weighs 1, therefore 2 hydrogen atoms weighs 2. So that 2 there, all I've done is just count the number of hydrogens in the formula. So half times 2 is going to be 1 gram. So that's my answer to the question here, what mass of hydrogen, okay? That question is exactly the same, just different numbers in a different equation. What is the relative formula mass of aluminium chloride? Okay, so relative formula mass is just looking at the formula and then adding up the masses of each of the atoms. Well, there is our aluminium chloride, okay? Now don't use that big 2 there, that's just a stoichiometry number. Okay, I often, I say to people, if you've got a twin brother or twin sister and you want to weigh yourself, you don't have to get your twin to stand on the scales with you. Okay, so don't use that big 2. Do not use that big 2. Aluminium chloride is AlCl3. It's got 1 aluminium and 3 chlorines. Well, 1 aluminium is 27, 1 chlorine is 35.5, but we've got 3 chlorines, so we need 3 of those. It's a bit long-winded to write it like this, but You would never get it wrong if you write it like that and stick it into your calculator and add it up. Okay? Good luck.